All right, Ivan, can you hear me okay?
Yes.
Great. All right, let's get started. Hello, good morning, everybody. I hope you're doing well and had a nice day off yesterday. Thank you for all the well wishes. I'm still a little under the weather, but I'm going to try my best not to lose my voice. Just a reminder that today you have your Chapter 4 quiz, so please make sure that you submit that at some point today. You'll have 1 hour once you open it. If you were unable to attend the Chapter 4 review session, it was recorded, and the link to the recording is on Moodle under the Getting Started heading. So today we are going to be going into Chapter 5, which is the last chapter that we cover for the course. And we sort of have a shift in how we're thinking about things. So in chapters 2, 3, and 4, we really ask the question, what is a derivative? How do we find the derivative? And what can we use the derivative to tell us, right? So maxes, mins, those sorts of things. Chapter 5 asks the question, what if we start with the derivative? What if we have that and we have information about the derivative? What will that tell us about the original function? So sort of going backwards now. And so I want to remind you that we do already know some information about how we can use information from the derivative to tell us about the original function. For example, we know that if the derivative is positive, the original function is increasing, right? From back when we were looking at graphs and things like that. But now we want to ask the question, well, increasing by how much, right? How much does the original function change? And so chapter 5 really looks to address those types of questions to sort of quantify that change overall when we're thinking about using the derivative to give us information about the original function. So I'm going to go ahead and turn on the dot cam. Okay. And so we're going to talk about distance and accumulated change. So we're going to start with this idea of distance, and we're going to use that as sort of a starting point or a jumping point to help us understand how we can take derivatives, aka rates of change, and use them to get information about the original function. So starting with this idea of distance, distance typically comes from physics, but you don't need to have taken physics to understand it. And so one way that we calculate distance is by doing velocity times time. So we have some rate of change, and we have some amount of time that we've been doing that rate of change. And if we multiply them together, that's going to give us the distance. So one example, if you were going to travel 40 miles per hour for 3 hours, how far did you travel, right? So 40 miles per hour is a velocity, miles per hour, it's a rate of change. 3 hours is a time. And how far did you travel? We want to know the distance. How far did you go, right? And so what this equation is saying is that if we take our rate of change, 40 miles per hour, we multiply how long we were going, that particular rate, that will give us the distance. So here we would do 40 miles per hour times 3 hours. The hours units are going to cancel. We have 3 times 40, which means we have 120 miles. So over that 3 hours, we traveled 120 miles, right? So we have some velocity times time. That's going to tell us how much our position changed, which is called the distance, right? So position was the original function. How much did our position change? 120 miles, okay? So that's how we would think about this algebraically. What we're going to bring in today is that we have a way that we can represent this graphically. And this is different than the types of graphs and the analysis work we've done before, but there are a lot of similarities. Okay, so we're going to put time on the horizontal axis, but instead of graphing distance, which is normally what we do, right? We have like the original function and time, we're going to graph the rate, right? So we're graphing the derivative. So our rate here, or the derivative, right, is this 40 miles per hour, okay? Now that is not a function that we typically graph, right? So we're graphing y equals 40, right? So it's a constant. So what we do when we graph a constant is we get just this horizontal line. So 40 looks like this, but instead of graphing it forever, we graph it for the amount of time that we are going this rate, right? So we do that for 3 hours, which means that from time equals 0 to time equals 3, our graph is just this horizontal line that represents this rate of 40 miles per hour. So I'm just going to put the units on the graph to help us remember. And so now what we're going to add to this, which is slightly new in how we think about graphing, is that we are going to look at what's called the area under the curve. Now, the word curve is a little deceiving because this is a line, but we're looking at the area between the line and the t-axis here. And you'll notice that that area is a rectangle, right? So if we want to get the area of a rectangle, we're going to do height times width. So we do 40 times 3, which is 120. Now you'll notice that that's the same as what we got up here multiplying. That's not a coincidence, right? So we're multiplying the rate times the time. And when we represent this graphically, since we have a rectangle, we have rate times time again, okay? And so this picture tells us the same information when we find this area as when we do this algebraically. Okay, so it's a new way to think about the same thing, right? So let's try another example now where we have 2 legs to our trip. So let's assume you were to travel 20 miles an hour for 3 hours and then 50 miles an hour for 4 hours. How far did you travel? So I want you to think about how we would compute this algebraically, right? Using rate times time, and then how we would draw a picture to represent this scenario using the same process we did here, okay? So I want you to take 2 minutes, see if you can figure this out, right? So again, both algebraically and with a graph, trying to figure out how far we traveled. The area on the graph should agree with the work that you did algebraically. And then in 2 minutes, we'll go through it together. Okay, take about 30 more seconds. Okay, so we see that our travel has 2 different legs, so to speak. So the first part, we're going 20 miles an hour for 3 hours. So I'm going to call this part 1. So 20 miles per hour for 3 hours, the hours units you're going to cancel, means that during this first part of the trip, we traveled 60 miles. And then we sped up and we were going 50 miles per hour for 4 hours. So for the second part of the trip, 50 miles per hour, 4 hours, hours cancel. We went 200 miles, which means that my total distance traveled would be the sum of these two legs of the trip. So 260 miles. Okay, so I have to pair each rate with the amount of time that I was at that particular rate and multiply them, and then I can add up the legs of the trip. Okay, now if I want to graph this, again, I'm going to have my rate in miles per hour. On the dependent axis, I'm going to have my time in hours. On the independent axis, and I look and I see that my total trip is 7 hours long, right? So I have 1, 2, 3, 4, 5, 6, 7. I'll label the 3. I know the rates that I'm working with are 20 and 50. So I'll count by tens. Make a graph here. Okay. And so if I want to draw what's happening, right, I need to consider this in 2 chunks, just like I did when figuring out the distances. So for the first 3 hours, I was going 20 miles an hour. So from time equals 0 to time equals 3, I was going 20 miles an hour. And again, if I find the area here, I do 20 times 3, which give me that 60, which is that first leg of the trip. Now, the second leg of the trip was 4 hours long. And so what I need to do is think about how I represent time. So the first 3 hours have already passed. So for the next leg of the trip, I start at time 3 when I speed up, and I go for 4 hours. So I go until time 7. Okay. Let me move that little hash mark over. So time 7. So that means now that my second leg of the trip is this rectangle over here, which is a rate of 50. That's the width here, or the height here, and then a width of 4 hours. And so 50 times 4 gives me those 200 miles. And I put them next to each other in the order that they are presented, because it was first I was doing this, then I was doing this. So I have this rectangle first, and then I've changed, and now I'm going at a new rate, so that one comes second. So if I were to have more legs of my trip, I would just keep adding them on based on the rates that I was going, one after the other, and I would add up the areas just like I added them up here to get 260 miles total. Okay, so hopefully that's starting to make sense. Now, we are looking at this right now through the lens of distance, which is velocity times time. And so I'm going to alter this a little to say total change equals rate times time. So what does that mean? That means we can do this for scenarios that are not just about distance and position, right, and velocity. We can do this with anything that has a rate of change. If we know how much a function is changing based on the rate of change and how long it's doing that rate of change, we can use that to talk about how much the original function changes. So let's look at an example that's not about distance, and I think we should easily be able to apply this process here. So suppose a population is growing at a rate of 2,000 people per year for 3 years, and then 3,000 people per year for 4 years. I want to know what is the total change in population over those 7 years. So instead of having 2 legs of a trip, we have 2 periods of time, right, where the population is changing. So I want you to take 2 minutes, see if you can apply what we were doing in example 1 to example 2 here, see if you can both find out algebraically what the change in population is, but also draw a graph based on this information. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. Okay. So the first change happens when we're going at a rate of 2,000 people per year. And we do that for 3 years. So we multiply the rate times the time. We see that years cancels, and we end up with a change of 6,000 people. Okay, that's the first rate of growth. And then we're growing at a rate of 3,000 people per year. And we do that for 4 years. So again, the years are going to cancel, and we get 12,000 people. So we add those two numbers together to get the total change in population, and we get 18,000 people. Now, there's a very important distinction that needs to be made here. That does not mean that our population is 18,000 people. It means that our population grew by 18,000 people. We don't know how many people there were to start with, right? If we knew there were 50,000 people, then we would add the 18,000 and we'd have 68,000 people. But we don't. What we know is how much the population changed. So the population grew by 18,000 people. How do I know it grew? Because the number is positive. We can have negative rates, and that will result in a decrease in the original function. But when your numbers are positive, it results in an increase of the original function. So again, this is not the size of the population, it's how much the population changed. So when we talk about accumulated change, we are finding out information about how much our original function changed over some period of time. Okay. Later on, we will add in things like the original size of the population, and then we will be able to talk more about those changes. But for right now, we are learning how to figure out how much something changes, okay, which is different than the actual value at a point in time. Okay, so how do we graph this? Right, we have rate, we have time. Our rate here is people per year. Our time is in years. I strongly recommend when you're doing this type of work that you're always labeling things with units, just so that you don't get lost when you're doing stuff. So our rate, let's do 1,000, 2,000, 3,000, right? Because we're talking about thousands. And then our time, right? 1, 2, 3, 4, 5, 6, 7. Okay, so for the first part, we have 2,000 people per year, and we have that for 3 years. So we end up with a rectangle. It looks like this. And then we bump up to 3,000 people per year for 4 years. So our second rectangle, we're going to put right next to it since that happens second. Looks like this. This was 12,000 people, and this was 6,000 people. So again, this is how we graphically represent what's happening, right, with this algebra. And so a natural question is, why do we want to represent this graphically, right? We can find these numbers and multiply them algebraically. So why would we want to graph it? And the answer is because this algebra only works if your rate is constant, right? So if your rate is changing and you have either a function that's, simple or hard, and you no longer have a number, then you can't just multiply, right? So if I said your function, your population is growing at a rate of t squared plus 2 people per year. Well, now we can't just multiply rate times time. So what graphing allows us to do is to extend this idea of rate times time, but evaluate it in a way that allows us to figure out what's happening behind the algebra when we have functions. Okay, what does that look like? So our next example here. Okay. Suppose the rate at which a skateboard is moving over a 60-second interval can be written as f of t equals 3t. So this is the rate now. So the rate is no longer constant. It's now a linear function, which means at time equals 0, the skateboard is moving 0 feet per second. At time equals 1, it's moving 3 feet per second. At time equals 2, it's moving 6 feet per second. So it's changing the rate based on this function, okay? I want to know what is the total distance traveled by the skateboard over the first 10 seconds. So we're still talking about distance traveled. If we try to do rate times time, we would be multiplying 3t times 10, and that would give us 30t. That is still a function. That is not a distance traveled, right? You might also think, well, can't we just take 10 and plug it into the function? Well, we could, but that wouldn't answer our question. That would answer a different question. If you take 10 and you plug it into this function 3t, that gives you 30 feet per second. That's how fast you're traveling at time 10. That doesn't tell you how far you traveled over 10 seconds. So we can't just multiply with our algebraic rules. Instead, we need to graph this function and try to approximate the area between the function and the x-axis using the things we know about geometry and about, what we were doing sort of with rectangles in the last couple of examples. So I want you to try this. I'm going to give you 2 minutes. Again, you want to graph your rate just like we were before. So instead of a horizontal line, you're going to have an increasing line. And then you're going to have to label your axes, which will help. And we're trying to figure out what's happening over the first 10 seconds using area under the curve. Even though it's not a curve, it's a line. Okay, so 2 minutes, try it out, see what you can figure out by applying what we've done before to this new type of problem, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so how do we approach this, right? So instead of having a constant rate, which is a horizontal line, we have the rate 3t. So if we were to graph 3t, what does that look like? We have an increasing line that looks like this. So if we want to apply the same sort of process that we did before, we would want to look at the area under the curve, even though it's a line, we're calling it area under the curve to include all functions, from 0 to 10. Okay, so that's the area we're trying to figure out. That's what we're trying to find. And so the question becomes, do we know how to do this, right? And so here we see that what has formed with this particular function, when we look at the area under the curve, is a triangle. And so we remember back that the area of a triangle, what's called triangle, 1/2 base times height. Okay, so the question is, can we figure out these variables? 1/2 base times height. So we have half. Now let's look at the base here. So the base of the triangle goes from 0 to 10. So we do know the base, and that's 10 seconds, right? The units of this are in seconds. And now what about the height? So the height of this triangle can be found by plugging a 10 into this function. That will give us the corresponding height in feet per second. So if we plug the 10 in here, we get 30 feet per second. So while we couldn't just plug in the 10 to find the final answer, it is part of the calculation we need to do. So notice here again that our seconds units will cancel, and we'll be left with 150 feet. So now we've taken this idea and process of graphing, and we've expanded it a little bit from constant functions to linear functions, right? If we have a rate that is linear, we can use triangles to also help us find this area under the curve. What becomes more complicated is when we have nonlinear functions, okay? Because when we have nonlinear functions, we end up with shapes that don't have geometrical representations that we commonly use, right? So if we have something super curvy and we want to find the area between 2 points, right? We could do arc lengths and try to figure out things like that, but that is far beyond the scope of what we want to do in a class that's not a geometry class, okay? So what does that mean for us? That means it's fair to make sure that you understand the area of a rectangle and a triangle. That's what we're going to be using. So if a function has a constant rate, we just use a rectangle. If it has a linear rate like this, we end up with a triangle, or sometimes a triangle and a rectangle. If there's also like a +5, that would shift it up, and you'd break it up into a triangle and rectangle. But how do we approach something like this that's not linear? So what we're going to do is we're going to come up with an approach that allows us to approximate the area under the curve using rectangles, and then we'll figure out how to use that to make the approximation better and better until we can get an exact area under the curve. So what does that look like? That means we're going to try to fit in rectangles. We are going to try to figure out a way to take our curvy area and just put in rectangles, right? That's what we know how to do right now, okay? So that's sort of our next step. We're going to move into thinking about how we approximate for nonlinear functions. And so in order to do that, we need to take a step back and think about the process sort of as a bigger picture. Okay, so the next example is going to help us understand the way this works. But this is a table question designed to help us sort of envision what's happening. So here's the situation, okay? Suppose that you are a bicyclist and you're in a race, okay? It's a flat road, you're in a race, and the race is that whoever goes the furthest distance in 10 seconds wins $1 million, right? Let's pretend the stakes are really, really high to make this really dramatic. So you're going to win $1 million if you go the fastest over 10 seconds. And somehow there's a mechanism on your bike that measures how fast you're going every 2 seconds. That's what's recorded in this table. So at time equals 0, you're still like stand still. The horn goes off, you start pedaling. At 2 seconds, you're going 5 feet per second. At 4 seconds, you're going 7 feet per second. After 6 seconds, you're going 10 feet per second. At 8 seconds, you're going 15 feet per second. And by 10 seconds, you're going 22 feet per second, right? And so the data gets downloaded, the judges look at it and they think, okay, we need a way to figure out the best way to think about how far this person traveled, right? So thinking about this, what we need to do is come up with a way that is methodical, right? That makes sense that someone else could apply to approximate the total distance traveled. It's really normal to want to just multiply each rate times time. But again, we have to think about what this represents. If we were to do that, if we were to multiply 22 times 10, that would mean we were going 22 feet per second for 10 seconds. But that's not what this table says. This table says that at time equals 10, you are going 22 feet per second. So we can't just multiply each rate times each time. So as I mentioned, the only way we know how to deal with things that are not linear, which this is not a linear function, is to fit in our rectangles. So how does that work? So what we're going to do is for each 2-second interval, right, from time 0 to 2, 2 to 4, 4 to 6, 6 to 8, we are going to assume that the rate is constant, right? That's what we did in the first couple of problems. We are just going to assume a straight line, a nice constant rate for each 2-second interval, okay? So here we have 2-second intervals. That's the way the table is set up. And so we're going to notate this as delta t equals 2. So we're computing what's happening every 2 seconds because that's the data that we have. So we start with time equals 0 to time equals 2. That's my first 2-second interval, right? So for this 2 seconds right here, time equals 0 to time equals 2, I'm going to do rate times time. I know that my time is 2 seconds, right? This is the 2 seconds. And I'm going to assume a constant rate. How do I assume this rate? Well, there's 2 different rates that are happening here, right? At time equals 0, I was going 0 feet per second. At time equals 5, I was going 5 feet per second. So I want to come up with a way to have a rate that is consistent for each time interval. So what I'm going to do is I'm going to pick the rate on the left. I'm going to pick the 0. So just, even if you have your doubts, follow me on this journey for a minute. So for the next 2 seconds, so time equals 2 to time equals 4. Again, that's 2 seconds. And I'm going to assume the rate on the left, right? Because I'm trying to be consistent. I'm always going to pick the rate on the left so that it's always the same type of process. So when I pick the rate on the left, that's time equals 5 feet per second, right? So we have 2 seconds, 5 feet per second. Now, from time equals 4 to time equals 6, again, that's 2 seconds. And then I pick the rate on the left, which is 7. And then from time equals 6 to time equals 8, that's 2 seconds again. And I pick the rate on the left, which is 10. And then last but not least, from time equals 8 to time equals 10, that's the last 2-second interval. I picked the rate on the left. So rate times time, 2 times 15. So then I multiply these numbers and add them up, right? Because I got to add up all my little legs. So this is 0, 10, 14, 20, and 30, right? So let's add these up. 30 plus 20 is 50, plus 14 is 64, plus 10 is 74, plus 0 gives me 74 feet. So when I approximate this way, my approximation is that you traveled 74 feet on your bicycle journey. Now, if you are this bicyclist and this is for $1 million, you are going to be very, very unhappy with the way I decided to do this, because I didn't even use your fastest time. I didn't use the 22. By picking the rate on the left each time, I used the rates starting at the very first rate, but I didn't use the last one, which was your fastest rate. This method that I just used is called a left-hand estimation. Okay. And the left-hand estimation in this scenario is really bad for you because it takes the slower rate of the two for each choice, right? We don't like that. So there's no reason why we can't also do a right-hand estimation, right? So for a right-hand estimation, we're going to do the same thing, but each time we're going to pick the rate on the right, okay? Which means that for the first 2 seconds, from time equals 0 to time equals 2, we're going to pick the rate on the right. So instead of 0, we're going to pick 5. Okay, so what I would like you to do is I would like you to complete this chart here and figure out how far we travel if we use a right-hand estimation. So for each 2-second interval, we're going to pick the rate on the right, then we'll multiply the numbers, add them up, and we'll see what the right-hand estimation is. So I would like you to take 2 minutes, see if you can fill out this and figure out what the right-hand estimation is, and then we'll go through it together and talk about what it means, what it tells us, and what other information we have. Okay, take about 30 more seconds. Okay. So here, from time 2 to time 4, if we pick the rate on the right, you have 2 seconds times the rate of 7 feet per second. From time 4 to time 6, do 2 times 10. From time 6 to time 8, we do 2 times 15. And time 8 to time 10, we do 2 times 22. When we multiply each of these smaller numbers together and add them up, we get 118 feet. So that is significantly larger than what we got when we did a left-hand estimate. So when we do this type of work, the bigger number we call the overestimate, and the smaller number we call the underestimate. And what does this tell us? This tells us that the actual distance traveled has to be between 74 feet and 118 feet. The actual area under the curve has to be between the overestimate and the underestimate. So sometimes we'll ask for the over and underestimate. Sometimes we ask for the left and right hand estimate. And so something that's really important is that the left hand estimate could be the overestimate or underestimate, depending on the scenario. It's not that the left hand is always the underestimate. It depends on if the function is increasing or decreasing or what the rate looks like. Okay, so if you're asked to find an over and underestimate, you have to do both left and right. The bigger one is over, the smaller one is under. And then we also have something called the best estimate. And best refers to the fact that it's our best guess based on the data we have. And so the best estimate is going to be to average these two numbers and find out what's in the middle. Okay, so if you're asked for a best estimate, you're going to take the over and under and average those two numbers together, and that will give you the best guess you have based on the data that you have. Okay, so now that we have a process to do this, we want to look at what it's going to look like if we are to graph this. Okay, so give me 1 second. I'm going to draw an axis here before I put it up on the screen to sort of see what I mean when I say that we're retrofitting rectangles in to help us approximate what's going on. Okay. So let's start by just setting up our graph, and I'll pull the data back up in a second. So we're going to graph our rate versus our time. Our rate was in feet per second, and our time was in seconds, and we were counting by twos. Okay, so we have 2, 4, 6, 8, 10. So we're looking over this 10-second interval. Okay, so when we graph this, there's two different graphs that we're going to superimpose here. We're going to look at the left-hand approximation and the right-hand approximation, because there are two ways to approximate the same information, and those are the two ways we've been looking at. Okay, so let's start by looking at the left-hand approximation. Okay, so we'll do that one in purple. So when we did the left-hand approximation, we said from time equals 0 to time equals 2, we were assuming a rate of 0. So that means that when we come over here to our graph, from time equals 0 to time equals 2, that we're going to draw right on that 0 line. There's no area. Okay. From time equals 2 to time equals 4, we assumed a rate of 5 on the left-hand approximation. So we come up to 5. It's a constant rate, so we assume it's constant for that little time interval. We know that that area is 2 times 5. We got a 10 there for that little time interval. From time 4 to time 6, we assumed a rate of 7. So again, by assuming this constant rate, this is what forces these little rectangles to sort of come to light. So that was 14 when we multiplied the 2 times 7. Times 6 to time 8, we assumed a rate of 10. So when we did 2 times 10, we got an area of 20. And then from time 8 to time 10, we assumed a rate of 15 for our left-hand approximation. Right, and we multiply those together, that area was 30. So this is exactly what we were doing in the first problem, where we had some constant and some amount of time we were at that constant. That's what we're doing here. We're fixing these to be constant rates, and we're letting that happen for each 2-second interval. So here again, our time interval that we're using is 2. And so 2 is the width of every single rectangle, right? So delta t equals 2 means that the width is 2. Since this is a left-hand approximation, that means that these leftmost points are touching the actual function in some way based on the data we have. This is going to be a little bit easier to see when we do the right hand. So when we do the right hand approximation, I'm going to superimpose this. We're going to do the same thing, and we're going to draw in our rectangles, but now we have new rates assumed. So for the first 2 seconds, we're assuming a rate of 5. So that's here. So that gives us an area of 10. From time 2 to time 4, we assumed a rate of 7. So that's a little bit bigger here, and that gave us 14. From time 4 to time 6, we assumed a rate of 10. Right, so that gave us a total area of 20. From time 6 to time 8, we assumed a rate of 15, which gave us 30 when we multiplied those together. And from 8 to 10, we assumed a rate of 22. So we're going to come up here, which gave us a total area of 44. Okay, so now that we've graphed this, we can see that the right-hand estimate is bigger than the left-hand estimate, right? We can see that those rectangles are taller. So the right-hand estimate is an overestimate. And so again, we can get an idea of what this function is going to look like by connecting these points. And I'll talk about this in a second. Okay, so when you do a left-hand estimate, your left-hand point of each rectangle touches the function. When you do a right-hand estimate, the right-hand point touches the function. So it helps us sort of get a sense of what this looks like. Now, if you think about the exact area under the curve, we can see that the red is an overestimate because we get more area than is actually under the curve. So the right-hand estimate is an overestimate. And then we can see that for the purple, it doesn't have all the area that we need to have the exact area under the curve. So this is an underestimate. So that's what's happening in the background when we do this type of approximation, is that we're getting these rectangles, right, by fixing the rate. Now, speaking of rectangles, when we talk about the number of rectangles that we're going to use to approximate, we use n. So if we count here either the left or the right's a little bit easier to see. We have 1, 2, 3, 4, 5. We used 5 rectangles to approximate here because there were 5 little 2-second intervals. So n is going to equal 5, the number of rectangles. Delta t is 2. It means we're counting by 2, which means the width of everything is 2. We also have endpoints. Okay, so we use A and B to talk about our endpoints. So A is your leftmost endpoint as defined by the independent variable, and B is your rightmost endpoint defined by the independent variable. And what we'll see is that there's going to be a relationship between A, B, delta t, and n. So let's formalize these particular variables and how we use them in this context. Okay, so, sorry, I'm dropping things over here. So what were the estimates we did? We did a left-hand estimate where we assume the rate on the left is constant for each choice we make. We did a right-hand estimate. That's where we're assuming the rate on the right is constant for each choice we make. There's the overestimate, which is where we compare the left and the right and we pick the larger one. And there's the underestimate, where we compare the left and the right and we choose the smaller one. Then there's also the best estimate, which is the left estimate, the right estimate divided by 2, or you can do over and under divided by 2. It's the same thing. But that's how you pick the best estimate. So that's what we've done so far. And so now we have these variables that we use in the context of doing this work. So we have delta t, which is the time interval for the approximation, and it's also the width of each rectangle. We have n, which is the number of rectangles we're using to approximate. And then we have a and b, which are the starting and ending points of whatever we're measuring, defined by the independent values. Okay, so these are all the things we're sort of working with and building up in our vocabulary to learn in this section. It turns out that there's a relationship, like I said, between these variables. And so the relationship looks like this, right? If you look at b minus a, which is the length of the interval you're considering, if you divide that by the number of rectangles that you want to use, you are able to find delta t. Or conversely, if you have delta t, you can use that to find the number of rectangles you will be using. Okay, so if you know the two endpoints and either delta t or n, you can use that to find the other one if you don't already know it. Okay, which can be helpful. We'll use that 2 examples from now. Okay, so thinking about all of this together, suppose now that we are still the same bicyclist race, but we find out that when we were measuring our data, that we also had the speed for what was happening at 1, 3, 5, 7, and 9. Okay, so the values at the even numbers are the same as the example we did before, but now we're adding in more information. Okay, so what we want to do now is we want to use this table to find the best estimate for the total distance traveled over this 10-second interval. And I want to know, is this a better estimate than the previous one, or is it worse? And how do we figure that out, right? So we're going to start, you're going to find the left-hand estimate by doing what we did in the last table. Notice here that delta t equals 1. So we're going to be counting by ones, which means every rate you multiply will be multiplied by 1. Notice that your a is 0 and your b is 10. That's the same as before, your starting and ending point. But if that is the same, but delta t has changed, that means that n will also change. So in the last example, n was 5. But now, if we do 10 minus 0 divided by 1, we get n equals 10. So if we were to draw this approximation after, we'd have 10 rectangles in the same span instead of 5. Okay, but what I want you to do here is calculate the left and the right hand estimate and use that to find the best estimate. And then we'll compare that to what we had found before to see if we think that's a better estimate or a worse estimate. So I'm going to give you 2.5 to 3 minutes. See if you can figure that out. Again, use the process we used when delta t was equal to 2, but now it's 1. See if you can work that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So for our left-hand estimate, each time interval is 1 second long. So we're going to be doing 1 second. And then for each interval, we're going to pick the rate on the left. So here we have 1 times 0 plus 1 times 3 for this next interval, plus 1 times 5, plus 1 times 6, plus 1 times 7, plus 1 times 8, plus 1 times 10, plus 1 times 12, plus 1 times 15, plus 1 times 18. When we do a left-hand estimate, we don't use the rightmost point. Okay, we use all of the rates except for the rightmost rate. So that's our span. So we know to stop at 18. And so when we add these all up, we get 84 feet. So now, right, in our approximation, our left-hand estimate says that we went 84 feet. And again, the numbers that are even were the same. The only difference is that we added in more data in between. For our right-hand estimate, for the first 1 second, we pick the rate on the right. We don't use the leftmost rate. So we have 1 times 3, plus 1 times 5, plus 1 times 6, plus 1 times 7, plus 1 times 8, plus 1 times 10, plus 1 times 12, plus 1 times 15, plus 1 times 18, plus 1 times 22. So again, we use all of the rates except for the leftmost rate, okay? And when we multiply those all together, we get 106 feet, okay? So let's start with the first question at hand, the best estimate, right? The best estimate is going to take these two and average them together. So 106 plus 84 divided by 2 is going to give us 95 feet. That's pretty close to what we got before. We had 96 feet as our best estimate. So how do we know which one is better? So notice here, if delta t equals 1 and n equals 10, that's what we were working with here. We know that our actual distance traveled has to be between 84 and 106 feet. When we did this before, we had delta t equals 2 and n equals 5, right? We're counting every 2 seconds. And we knew then that our distance had to be between 74 and 118 feet. So the current approximation has a smaller interval, which means it's a better approximation, right? So there's only 22 feet between 84 and 106. It's a span of 22. Whereas here, the span is going to be 44, which is much, much larger. So that means that this is the better approximation. So what does that mean in general? It turns out that in general, if you can make your delta t smaller, that means that your n will be bigger. You can fit in more rectangles. That's going to make your approximation better. Okay, so file that away for a minute, that we want delta t to get smaller and n to get bigger. Okay, we're going to come back to that. But before we do, we want to do one more problem that really links in this idea of delta t, of n, of over and under estimates, and what that means when you think about the data altogether. And we're going to do one more problem that asks you to think about these definitions and we're going to do it with a graph. Okay, so so here we have a picture that shows the velocity of an object over 31 minutes. Okay, so we don't know what the object is, but we know that, at time equals 31, it's moving at 0 feet per second or whatever you want the units to be. And at time equals 0, it's moving 20. Okay, we want to figure out the total distance traveled using a left-hand sum with n equals 2. And we want to figure out the total distance traveled with a right-hand sum with n equals 2. So how do we do this with a graph? What does the n tell us? How do we structure a left and right-hand approximation with n equals 2 based on this particular picture, which gives us information about the velocity of an object? Okay, so what I want you to do is I want you to figure out what is A, what is B, what is n, which is given, what is delta t, and then how do we use that to approximate these distance traveled using left and right hand sums, right? So we're drawing in rectangles to make this work, but how do we draw them based on this information? So I'm going to give you 2 minutes to try this out. I want you to think about, what we know, how to put it all together, what it means, and do your best to try to figure out how we might fit that into this type of problem. And then we will go through it together. Okay, take about 30 more seconds. Okay, so thinking about these pieces of information, which is often what we need to solve a lot of these problems, our A is where our independent variable starts, which is 0, and B is where it ends, which we said was 31. That's also given in the problem, right? So that's in minutes. So n for both of these is going to be 2, right? We're asked to do this with n equals 2. And so we can find delta t by doing 31 minus 0, b minus a, divided by 2, which is going to give me 15.5. So what does this all mean? It means that I'm going to be using 2 rectangles to approximate, and each one is going to have a width of 15.5. So I'm dividing this up into 2 at 15.5, which is about the halfway point. So I'm going to mark that roughly here, right? And so no matter which approximation I'm doing, I'm talking about having a width of 15.5. Okay, so let's start with part A. Let's start with a left-hand sum. If we're doing a left-hand sum, then I have to take my first interval, 0 to 15.5, and I'm using the left-hand point, which is 0, to dictate the height of my rectangle. So I'm going to go up until I hit the function, which is at 20, and I'm going to assume a constant rate for that interval. So I get this rectangle that looks like this, right? Where again, the left-hand point is what touches the function. So here, the area of this rectangle is 15.5 times 20, right? So the time times the rate. If I multiply those two numbers together, I'm going to get 310 for the area of that first rectangle. Now for my second rectangle, I'm looking between 15.5 and 31, right? And I'm picking the one on the left. So when I think about the height of my second rectangle, I take the 15.5 until I hit the function. And that is my constant rate between 15.5 and 31. So I do have to do a little approximating here to figure out how high I think this is. For me, it looks like it's a little tiny bit above the halfway point. So I'm going to use a height of 17. You may have used 16 or maybe even 15, but it looks a little tiny bit above to me. But it just matters where you put it, but it should be in that general range. So here, the width is 15.5. I'm using 17 as the height, but this might be different for you, right? You might have said 16, that's fine. And that gives me 263.5 for my second rectangle, which means that my left-hand approximation is going to be to add these two numbers together, which is going to give me 573.5. Okay. Now, when I do my right-hand approximation, I'm going to do something similar, only now 0 to 15.5, I'm going to use the 15.5 to give me my height of my first rectangle. Okay. So now, when I think about that, I'm going to do 15.5, which is my width, times, again, I'm using 17 because that's what I approximated this to be, but you may have used 15 or something near there. That's fine. So when I multiply those together, I get 263.5. So that means that my right-hand approximation for the first rectangle is 263.5. Now for the second rectangle, again, I have 15.5 and I have 31. 31 is the right-hand point, and that has a height of 0, right? So that's just right on the line. So there's no area here. So I'm just going to write 15.5 times 0 to help us remember, which is 0. So my right-hand estimation is going to be 263.5 plus 0, which is 263.5. So knowing how all of these variables interact with one another helps us understand how to find the information we're looking for. If we did the same thing with n equals 4, n equals 10, n equals 20, right? We'd be fitting in many, many more rectangles, and our approximation would get better with each iteration. Okay. Okay, so we are not going to have time to finish the last two parts. So what I'm going to do is I'm going to set up example 5 with you so you know how to get it set up. And then you should watch the lecture video to see how to finish it. And then also the lecture video on the last part example, which is Riemann sums. So let's talk about this example and how we set it up. So if T is in hours of a 20-hour period, the rate at which bacteria grows is given by, f of t equals 3 plus 0.1 t squared. Find an over and under estimate of the total change in bacteria over this period if delta t equals 4. So we'd have to do something similar to the graph here, where we're really thinking about what is A, what is B, what is delta t, and what is n, right? So what are we given in this problem? We're given that delta t equals 4. Now, what about A and B? So here, our independent variable is time. And so we have a 20-hour period. That means we're going from time equals 0 to time equals 20, right? Which means that we can find n by doing 20 minus 0 divided by 4. So n equals 5, right? So this is all the information we need to get set up. So if we're looking for an over and under estimate, we are going to be doing the type of work we were doing with the table from before. The difference is we don't have the table yet. So what we need to do is generate our table. What does that mean? So we start at time equals 0. That's our starting point. And we get the corresponding rate by plugging a 0 into the rate function. This function is giving us the rate of change. So if you plug in a 0, you get a rate of 3. Now, delta t equals 4. That means that we are counting by 4s. So 4, 8, 12, 16, and we go until 20, right? So b equals 20. So we are going to plug each one of these into the function. This will be 4.6. And once we have all the rates, then we're doing the left-hand estimate and the right-hand estimate, just like we did in the previous table examples by doing things like 4 times 3, 4 times 4.6, 4 times whatever this rate is. We'll have a left and right approximation. And from there, the bigger one is an overestimate and the smaller one is an underestimate. Okay, so you should be able to finish up this problem and then you can check your solution on the video and then also watch the short video on Riemann sums and then you will be good to go. Okay, don't forget to take your chapter 4 quiz today. Otherwise, have a great rest of your day and I will see you on Thursday.